Okay, so good morning, everyone. So today we want to continue our discussion of the design and the analysis of columns. Okay, so for columns, we said you can have 5 columns or spiral columns. Okay, so we are actually starting by the understanding the purpose of spirals and how spirals reinforce concrete column. Okay, so here what we said last time. So for what we're talking about now is the spirals. Okay, design of spirals. So the purpose of spirals, okay, or one of the important functions of spirals or spiral stirrups is when you have a column like this. Okay, usually it's a circular column, and then you have your spiral. Okay. This spiral will reinforce the core of the concrete. So if I take a cross section here, okay, the length over which this spiral repeats itself is S, the pitch here. If I take cross section, the cross section will look like this. That's the cross section. Okay, that's the outside of the concrete. And then you have your spiral stirrups. And then inside that is the core of the concrete. So I have a cover outside the spiral, and then what's inside is called the core of the concrete. So here, this is the core of the concrete. Okay, the area of that is AC, the area of the core of the concrete. Okay, so when you have this spiral stirrups, okay, the spirals will be able to confine, okay, if I take just 1/2 of that section here, okay. So this is what we get. I'm just going to copy it. Paste it here. Just 1/2 of that, applying an axial force, a longitudinal force on that column. Okay. The spirals will be under, there will be hoop stresses in the spiral. We discussed this last time. I'm just redoing that again. Okay. In a slow way. There will be some force, tensile force in this hoops. In those spirals, tensile hoop stresses, okay? And that will be confining the core of the concrete. So here the stress is F yield. This is the maximum stress that can be reached in those spirals. And this will put a confining stress on the core of the concrete. We're going to name this F2. That's the stress. So at equilibrium, we're always at equilibrium here. The force in the spirals, the tensile force in the spiral is equal to the force of confining on the core of the concrete. Okay? So how much is the force in the spirals then? You have 1 here and 1 here, so you have 2 F yield multiplied by the area of the spiral, okay? And that is equal to the force generated in the core of the concrete, which is the stress F2, multiplied by the area over which this F2 is applied. So how much is the area over which this F2 is applied? It's this width multiplied by S, right? So D core multiplied by S, the pitch. Okay? So now, F2, the confining stress, the maximum confining stress that this theorem can provide is 2 F yield, the area multiplied by the area of the spiral, divided by D core S. That's the maximum confinement that the spiral can provide to the core of the concrete. This is the confinement stress. It's a function of the area of the stirrups, the spacing or the pitch, and D core. Okay? That's F2. So let's have this for a while. We're going to use it in a moment. Now, last time we said to express how much stirrups do you have, for any steel we use rho, the steel percentage, okay? For the longitudinal steel bars we use rho as the percentage or the ratio between the areas, okay? Now for spirals, okay, rho is the volumetric ratio. For the spiral stirrups, rho for spirals is calculated based on the volumetric ratio. So what does this mean? Rho S is the volume of steel in one loop divided by the volume of concrete in one loop. So the volume of steel in one loop, that's the area, multiplied by the length, which is by the core minus D of the spiral. Okay? You can neglect this part over here compared to the core, the diameter of the core of the concrete. Okay? Divided by the volume of the concrete in one loop, which is the area of the core, okay, by D core square divided by 4 multiplied by S. So this D cancels with one of those D, so here you have 4 and the pi cancel with the pi, so here this cancels with this one cancels with the DC, sorry. So here you have 4, the area of the spiral, divided by SDC. So that's rho S. This is the rho of the spiral. The percentage of reinforcement in the, certain direction of the circumference. Okay? So 4ASB divided by SDC. Now, as you see here, comparing those two equations, here you have 2ASB divided by DCS, 4ASB divided by SDS, DC. So I can actually move this part over here and put 1/2 rho S, right? So this is equation, let's say this is equation 1, this is equation 2. So combining equation 1 and 2, you're going to find that F2, the confining stresses, is F yield rho S divided by 2. Okay? That's the confining stresses. The maximum confining stresses due to the effect of the spiral. Okay? Now, when you confine the core with this magnitude of stress, okay, that will increase the axial stress that the concrete can resist. Okay? You remember that curve that we showed in chapter 1? Let me show you that in chapter 1. Actually, I'm sure that you forgot that, but in chapter 1, we discussed the effect of confining. So when there is no confining stress, let's say the Fc prime is around 4 KSI. When you have a confining stress, that's a confining stress. Okay? When you increase the confining stress, Fc prime increases. Okay? The stress in the axial direction increases. Fc prime, the maximum stress that the concrete can resist in the axial direction, increases. Okay? So actually that's what we have now. You have a confining stress of F2, right? You're confining the core of the concrete with that magnitude. So the stress, okay, the longitudinal stresses will increase. By how much? So F2 will result in an increase of the axial strength by magnitude of F1. How much is F1 from experiments? Okay, F1 is approximately equals to 4 times that F2. So you put a stress, the confining stress of F2, the axial strength of the column will increase by 4 F2. Okay? So that's great. So the increase in the axial stress will increase by the magnitude of 4 F2. We already have this equation for F2, so it's 2 F yield rho S. So that's the increase in the axial stress once due to the confinement of the core of the concrete. Okay? Is this clear for everyone? Okay? Okay. Now, the design philosophy for spiral columns, okay, is different from the design philosophy of tied columns. Okay? The ACI code requires that when you have a spiral column, okay, you make use of that confinement stress, that, added strength. Okay? So let's see here. Okay, let me open this slide for chapter 9. So now, when we have a column, okay, you have a column, that's a column, that's a longitudinal, you apply a normal force, okay, whether that column is rectangular like this or circular, okay, you have some ties, either separate ties like this or spirals. You apply normal force. The way the columns collapse, okay, is that you have this outer portion. There is no confinement for that outer portion, right? It's not confined. The confinement comes from the stirrups, right? That's what confining your concrete. So definitely this cover over here, this cover or this cover over here is weaker than the core of the concrete. Okay? Those covers are weaker than the core of the concrete. So when you apply normal force and you keep increasing that normal force, increase it till you reach some maximum value, okay? What will happen is that core, cover will collapse first, right? So you're going to have that cover collapse or, get cracked and fall off first, okay? Just the cover. Okay? For tight columns like this, okay, once the cover collapse, okay, the area inside the core, okay, or the total area of the column becomes less, okay, so the core of the concrete will not be able to resist that force, and then the column is going to collapse, okay? While here, for this spiral stirrups, the ACI code wants you to make use of the spirals to prevent the column from collapsing when this cover, okay, collapse or spell off, okay? So now, when the cover collapse, okay, you lost that area. You lost that green area, right? But there is confinement on the core of the concrete, so the core of the concrete can now resist more force, right? Because it's confined, okay? So actually the ACI code wants you to design those spirals so that they can prevent or they can provide an added strength to the core that will be equal to the strength provided by that collapsed cover. So to do this, let's find how much was the force supported by that cover, okay? And we want the core now to be able to resist the force that was resisted by that cover, okay? So how much is the force resisted by the cover? So now for spiral columns, once the cover spell off, the core should provide an added strength that substitutes the strength of the cover. Okay? Is that clear? So how much is the strength of the cover? How much is the strength of the cover? The force that the cover can hold. How much is the magnitude of the force that the cover was resisting? The area of the cover, right? Multiplied by the stress, which is 0.85 FC prime. Okay? So the area of the cover is the area gross, the area of the column, minus the area of the core. That's the area of the cover. Multiplied by the stress, which is 0.85 FC prime. That's the strength of the cover. This strength of the cover is equal to, should be equal to the added strength by the core. So that's AG minus AC multiplied by 0.85 FC prime should be replaced by the added strength. How much is the added strength to the core of the concrete? How much is the added strength? It's F1, that's the added longitudinal strength, right? Due to confinement. It's F1 multiplied by the area over which this F1 is applied. F1 is applied on the core of the concrete here. So it's F1 multiplied by the core area. So F1 area core. Okay? And F1 was equal to 2 F yield rho spiral. Okay? And here you have AC. So in order for the spirals to provide this added strength, let's find how much is rho S that will enable the column to actually have that added strength. So finding rho S here, getting that to one side of the equation, you're going to have 0.425 FC prime divided by F yield and area gross minus AC divided by AC. Right? So if your rho spirals, the amount of spirals you're providing is equal to that magnitude, so actually the core of the concrete will be able to replace the cover, okay? But if it's less, it won't be able to replace the cover, and then you're not making use of the confinement, okay? If it's larger than this, that's fine. The confinement is larger than actually what is required, so that's good, okay? So this equation, okay, is modified a little bit in the ACI code, okay? It looks the same, but in the ACI code, the factor here is increased a little bit, okay? So in the ACI code, rho S required, okay, is the same equation that we just derived right now, except that instead of 0.425, it's 0.5. So that's the amount of spirals you should provide so that the spirals will be able to confine the core of the concrete, so the core of the concrete replaces the cover once it collapses. This equation is in the ACI code. It's equation 25.7.3.3. You don't have to memorize it. It's in the ACI code. You just need to know where it is. Okay? The equation that you have to memorize is how much is rho S. Rho S over here is that equation. It's 4 area spirals divided by SDC. Okay? So now, that's the design of the spirals. So the spirals in a circular column, okay, has to adhere to that equation. Okay? Its spacing or its pitch, the S, the area of the spiral has to be calculated from this equation, because as you see here, rho S, this rho S is simply from that equation that we just wrote, okay? Rho S is 4 ASP divided by SDC, sorry. 4 area spiral divided by SDC. So from those two equations, you can design your spirals according to the ACI code. Okay? You find how much spiral stirrups you should provide. As you see here, you have two variables, area spirals and S. Okay? So you will assume one of them and find the other one. Okay? Assume, let's say, the area of the spirals. Okay? And find S. Okay? So there are some requirements. I'm just going to go through those requirements in the slides over here. I have it in the slides for you. Once you design those spirals, there are some requirements over here. Let me show you that, okay? The spiral diameters, once you have it, it cannot be less than number 3, okay? You cannot use less than number 3 bars for the spirals, okay? And the clear spacing between spirals, S, cannot be less than 1 inch, and it cannot be greater than 3 inches, okay? So that's the limitation of S and the diameter of the spiral, okay? So the diameter is limited to 3/8, it cannot be less than 3/8, and the clear spacing S cannot be less than 1 inch and cannot be greater than 3 inches, okay? Another requirement for the spirals, okay? Okay. For spirals, okay, the number of bars that you should provide, okay, should be at least 6 longitudinal bars, okay? You cannot provide less than 6 longitudinal bars, okay? What are other requirements? The other requirements are for tied columns. For tied columns, okay, you should have at least 4 longitudinal bars, okay, with tied columns, okay? If you have a tied column, even if it's a circular column, but it's ties, it's not spirals, you should use at least 4 longitudinal bars, okay? So those are some requirements. If you use tied columns, okay, the ACI code gives you some requirements for the ties. The ties should not be far away from each other, okay, so that they can prevent buckling of the longitudinal bars, okay? Because that's a very important, you know, collapse mechanism in columns, okay? You apply this longitudinal force P, okay, this axial force P, and this column collapse like this. Those longitudinal bars buckle. They are under compression. Those are very, you know, cylinder bars, okay? The cover here that was supporting them will actually collapse. That's good because it's not confined, so it's going to collapse first, and that will leave those longitudinal bars unsupported, so they will just buckle like this, and then failure will happen, okay? To make sure that buckling is restrained to a certain limit, this spacing between the ties is limited, okay? So how much is the spacing limitation? The spacing limitation is, the spacing limitation, the spacing,
1 to 3 inches.
no, it's 48 multiplied by the diameter of the stirrups, or 16 multiplied by the diameter of the longitudinal bars, or the least column dimension. I just want to have this to show it to you. Yes, over here. So for tied column, the maximum tie spacing is the smallest of 48 multiplied by the bar diameter, or 16 multiplied by the longitudinal bar diameter, or the least lateral column dimension, okay? So the spacing of the spirals, the spacing of the ties is limited to those values, okay? So that buckling of the longitudinal bars in the column does not happen. The diameter of the ties, okay, if your longitudinal bars are number 10 and smaller, okay, then the ties should be at least number 3. If it's larger than number 10, and for bundled bar, the ties, okay, should be at least number 4 or higher, okay? That's similar to what we had in the beams, okay? So those are some requirements for the design of the ties or the spiral, okay? So for the spiral, there is an equation that you have to fulfill. For the ties, and then once you find the spacing of those spirals and the diameter of the spiral, there is some limitation. The spacing of the spirals is limited to 1 to 3 inches, and the diameter is 3 inches of the spiral. For the ties, there is no equation to design the ties, but there is a limitation for the spacing of the ties, okay? That comes from here, and there is a limitation for the tie diameter, okay? It's either number 3 if you have number 10 or less, or number 4 if you have the longitudinal bars being larger than number 10, okay? Any question? So now, actually, we dealt with the design of the transverse steel. So what we learned so far is how to design this transverse steel, whether it's a tie or a spiral, okay? Now, what about the design for the longitudinal bars, those longitudinal bars, how to design for this, okay? So now, if you have a column like this and there is a force P, let's say P ultimate applied on that column, okay? you want to design that column to be able to resist this P ultimate, okay? That's so simple, okay? I left that to the end because that's so simple, okay? Design of columns to resist P ultimate. Actually, when you have a longitudinal force like this, it's going to be distributed among the two components of the column. What are the two components of the column? Concrete and steel. So that P ultimate should be resisted by both P concrete and P of the steel. And definitely you have a phi here, right? So how much is the strength of the concrete? How much force can the concrete resist? Force is equal to stress multiplied by the area. So the stress in the concrete, it's 0.85 Fc prime multiplied by the area of the concrete, which is area gross, the area of the column, right? But minus the area steel, because not all the area is concrete. You have some steel in it, so you just have to subtract the area of the steel. And how much is the force that can be resisted by the steel? F yield multiplied by the area of the steel. As you see, it's that simple. That's the design equation, okay, for the column in the longitudinal direction, okay? How much is phi? If it's spiral, then it's 0.75. If it's tight column, it's 0.65, okay? So is that the equation that we're going to use? Not exactly. We just have to add, okay, another factor. It's the same equation that we have here. I'm just copying it. I just have to multiply it by a factor alpha. Okay? What's that factor alpha? Why do we need the factor alpha to add to that equation? So the thing is, we have our column like this, okay? And we're assuming there is an axial force, P ultimate. Only an axial force, okay? If you only have an axial force, that means that that axial force is just right at the center, is applied at the center of the column. Okay? Actually, when you build your structure, okay, there might be some mistakes in building the structure, so this P ultimate might have some eccentricity. E, small eccentricity, accidental eccentricity, okay? It's not intended, but it's due to, you know, the beam is not oriented directly over the center of the column, so you might have this small accidental eccentricity, okay? So this factor alpha, just to account for any accidental eccentricity that might happen, okay? So alpha is to you know, account for that accidental eccentricity. How much is alpha? Alpha is 0.8 for tied columns and 0.85 for spiral columns. So actually you have those two design equations in the ACI code providing alpha and phi. So here you have, this is phi and alpha, and multiplied by 0.85 FC prime area gross minus area steel plus F yield area steel. That's the design equation for spiral columns. And the other equation is for tight columns. The factor of safety of phi here is 0.65, and this is 0.8, and you have the same, the rest of the equation is the same over here. So that's for tight columns. I can see that, you know, those two equations are so simple you can memorize them, but anyway, if you don't want to memorize them, those are equations 22.4.2.2 with table 22.4.21 in the ACI code. Okay? So that equation will help you design your column, okay, or will allow you to design your column. As you see here, to design the column, you need to find its dimensions and the amount of steel to put in it, right? So you only have one equation that has those two parameters. Area gross is the area of the column, and area steel is the area provided by the steel, right? So you only have one design equation with two parameters. So you either select maybe a row and find the area gross, or you can assume dimensions and find how much steel would fit with those dimensions that you are using. Okay? So you cannot just design for both, okay? You just have to assume one of them, okay? Or start with knowing one of them and then find the other one. Okay? Once you find those area steel and area gross, there are some limitations by the ACI code. Okay? So what are those limitations? Let's have them here. Okay? So here are those some limitations. The percentage of longitudinal steel may not be less than 1% and cannot be more than 8%. So area steel, once you find area steel from that equation, dividing it by the row, dividing it by BD, okay, it will give you rho. Rho cannot be less than 1% and cannot be larger than 8%. Okay? Here, about this regulation, there is a very important thing. This number here, 8%, might be misleading sometimes. Why? Why? So the first question is, why does the ACI code require, that maximum 8%? The longitudinal steels cannot be more than 8% of the area of the column. Why? Why do you think the ACI code put that requirement?
So there's warnings? Warning before failure, maybe?
No, because the way the column works, it's not like the beam. The beam, the more steel you put, the strain is going to get less. But here, the more steel you're going to put, it's an axial stress, you're going to have the same strain. It's not going to have any effect on the strain. The ACI code, no. You can actually build a column made out of steel, right? Completely. It's your choice, right? Yes. So the thing is, to be able to cast your concrete, right? The more steel you're going to have, the more conjected, the bars are going to be closer to each other, and the concrete will not be able to pass through those bars, right? So that's why you have this limitation of 8%, so that the concrete can pass through the bars, okay? When you cast that concrete in place. So now, why is that misleading? You now understand why this 8% is required, okay? When you have a multi-story building, like the one that we are in, how is that build, okay, you have to understand how the method of construction. So you have a building, you have slab here and columns here, okay? So how you're going to build this, you're going to start building those columns, okay? And you have some longitudinal bars here. And once you build those columns and cast them, you're going to cast the slab here, that floor. And then you're going to start casting that column over here, those columns. There must be continuity between the column in that floor and that floor, okay? In those two floors. How to achieve those continuity, you actually have those bars extended like this, okay? And then the steel or the reinforcement in the top column is going to have an overlap here between them, okay? Is it clear for everyone? So actually, if you're providing 8% of steel here, how much the percentage of steel here? It's 16, okay? So actually, if you have a multi-story building, okay, it's not 8%. How much would that be? 4. So that when you have doubling the steel here, when you double the steel here, you're limited to the 8%, okay? So the ACI code says it's 8%, but if you have a multi-story building, to adhere to that 8%, you have to move it down to 4% because of the overlap that you're going to have here, the anchorage that you're going to have here, okay? So that here, that figure shows you, the overlap. So actually here you're going to have double the area of the steel in the overlap area. So that's one limitation. The area steel or raw steel is limited to 1 to 8% in just one single-story building, but it's limited to 1 to 4% in multi-story building. We discussed this. At least 4 longitudinal bars must be used within rectangular or circular ties. At least 6 longitudinal bars must be used with spiral ties. And then here the practical column dimensions is about 8 to 10 inches, and then you use multiples of 2 inches. Okay? When you find the dimensions of the column, let's say you need a diameter of 16.5. No, you don't use 16.5. Just maybe use 15 or 16, 18. Okay? Another requirement by the ACI code for the longitudinal bars, okay, you need to have 1 bar at the corner, at least, so 1 bar at each corner, okay? And then let's say you need more bars, not just 4, so you're going to add more bars inside here, okay? Those bars, okay, should each bar here, or each alternative bar, okay, should be surrounded by a tie or steel, okay? And that tie should make an angle of at least 135 degrees, okay? So this bar here is not surrounded by a tie or steel that goes by an angle that is less than 135 degrees. Is that allowed by the ACI code? Yes, as long as the distance between those 2 bars is less than 6 inches. So you don't need to provide a stirrup that goes around that bar. But this is only for every alternative bar. So the thing is, let's say, let me draw this. You have a column that looks like this. And you have your stirrup. And those are the longitudinal bars. And you actually need to put all those longitudinal bars in the column. If this distance is less than 6 inches, so you don't need to provide the stirrup here. But you can only, allow this alternative bar not to be, confined by stirrup, okay? But this one, so you already left this without stirrup, you have to have a stirrup here. So I need to provide a stirrup that goes around that bar here. And then I'm holding this one. I can allow this one not to be supported by stirrup as long as the distance is less than 6 inches. Okay? What if the distance is larger than 6 inches? What if those distances are larger than 6 inches? If it's larger than 6 inches, so you have to provide stirrups to support them as well. Okay? So that's what we have here. For tied columns, ties must be arranged so that every corner and every alternate longitudinal bar has lateral support provided by a tie bent around the longitudinal bar with an included angle not greater than 135 degrees. No longitudinal bar can be located more than 6 inches from such a laterally supported bar. And here we have some figures representing this. This distance cannot be more than 6 inches, okay, in both directions. If you have this distance larger than 6 inches, so you need to provide a stirrup in the other direction. If it's larger than 6 inches, so you have to provide a stirrup in the other direction. If you need to provide a stirrup in this direction, you can remove those and put stirrup that goes down in that direction. Okay? Here you have this one. If this is still less than 6 inches, so you can, leave this unsupported and then provide spiral over here. Okay? Any questions? So those are all the requirements for designing and analyzing columns. Next time we're just going to solve 2 examples. Okay? Before you leave, I have your homeworks over here. You didn't give me your homework.
Which one was this?
Fedor? Huh?
Yeah. I turned it in.
James, Dylan.
Dude, I turned it in. You saw it.
I know you did, because you go, Tristan, you have time to fix it.
Yeah. That's the one I went to visit you in the office for.
I don't know, those are the only ones I have. Is your gate posted on blackboard for this one?
I don't know. But it's the one that I came to your office. You saw it was done. Remember? It was like 5 o'clock in the afternoon.
Yeah, okay, but I don't know why.
He doesn't have it.
I swear I turned
He
it in.
did turn it in.
He turned it in.
Yeah, I'm not questioning that. Okay, but I don't have it. That's the point. The TA didn't give it back to me, or maybe I have it in my office. Let's go now to my office. Maybe I just didn't pick it up.
You freaking tear you out.